It's very interactive. So during any time, if you have any questions, just stop me there and I can just go over it. So what I want to cover today is uh, how large scale recommendation systems like, let's say, LinkedIn feed or LinkedIn notifications or Facebook feed, how are they built and how they are managed. And when you are using machine learning, how do you get the things working uh, in a large system like LinkedIn feed or Meta feed, right? There are many models that are running, which is serving our feed experience and improving our feed experience. And how does a team of, let's say, 100 engineers, 100 ML engineers, what kind of things they have to do behind to make sure the improvements on the feed experience keep going on. Uh, So yeah, my goal is to take two broad use cases. One is a feed and one is a notifications. Both of these examples, they're motivated by LinkedIn, but the ideas apply to any other systems, any other recommendation systems, including like Pinterest or Meta or any other company. Uh, okay, so I'll get started. So as you can see, I'm showing you a LinkedIn feed over here, and members come to the LinkedIn feed to build their professional community and to stay connected with the people whom or to connect to new people and to consume content that they are interested in. If you look at broadly what you will see on the feed and on a LinkedIn feed, you will see shares by members. So members who are sharing their activities. You may also see a jobs recommendation. You may see articles, you may see ads. Now, the top three are organic content. I mean, assuming jobs is also organic, but some jobs are also, there is also a paid version of those jobs. But ads is not an organic content. So you see a mix of organic and content which is giving us revenue. Uh, I'll go into what are the metrics LinkedIn cares for when they look at the feed experience. So let's say you have a feed experience today, any experiments you do, what are the key metrics that will decide whether an experiment is successful? So the first one is viral actions, second one is job applies, and the third is engaged feed sessions. Viral actions is nothing but the like, shares, and comments, the total number of like, shares, and comments. And the goal is basically, if I can get more people to do these actions, that will lead to more activity, which will again let flow into other people's feed, and then they would do an activity on it, and hence the whole thing will continue. Job applies, obviously. I mean, it's clear. If I'm recommending you a job, it better be relevant. You better apply for it. Um, Engagement on a feed session, I think this is a subtle one. So you want to know whether the member engaged in a session and how long did the member engage in the session. So these are again three metrics. These are nothing to do with machine learning models, just to be clear. This is just a metrics that define the success of how we evaluate the improvement in product. And now we come to the machine learning models. And for simplicity, I have tried to abstract the problem, and I've only looked at like 3 ML models. In reality, there are like a combination of more than 10 models. But whatever math we see over here applies and can be generalized. So for a member M and an item U that you see on the feed, there's a score we compute for every item. We call it S of MU. This score is a combination of a model, probability of a VA. VA is a viral actions model, which is combined with probability of EFS, which is combined with probability of job applies. And as you can see, XEFS and XJA, these are hyperparameters that are used to decide the weights of these models or the scores of these models. So if you think about it, if I, let's say, set the scores of, so so let's say you go to the field, what's happening at the back is we have 500 items which we want to show to you. What is the ordering of those items? The ordering of those items is decided by S of MU. So you will have 500 scores, and the topmost score will go at the first slot, and so on. Now, if you see, if I set XEFS and XJA to 0, we are purely optimizing for viral actions. So you will have a ranking which will only optimize for viral actions. And similarly, different choices of XEFS and XJA will lead to a different ranking and hence a very different metric. So the question is, how do you choose XEFS, XJA, where you care about the below optimization problem, which is maximizing the viral actions, given EFS greater than some constant CEFS, job applies greater than some constant C of JA. And if you see, the viral actions is a function of X. X is nothing but those combinations of hyperparameters, XEFS and XJ. And EFS similarly is a common. So basically what I'm saying is a given choice of XEFS and XJ determine an operating point and will give you a different metric. Your VA would depend viral actions. So viral actions is a metric below, just to make sure everyone everyone is on the same page. Whereas this one, P of VA, is a machine learning model. These two are very different things. Please ask questions if something is not clear. I can't see you, but if you ask me a question, I'm happy to clarify. And things will depend a lot on this. If you don't get this, stop me here. Happy to clarify. But going back, V of VA is a function of X. EFS is a function of X. J is a function of X. Hopefully that point is clear.
Well, just a quick question. So the ranking function, how is it determined from the previous slide?
Your voice is breaking. I'm sorry. Can you repeat your question, please?
Is it fine now?
Yeah.
Okay, still it's like.
No, I can hear you. Please speak up. Yeah.
No, I was just trying to connect the previous slide from the current slide.
Yeah, so that's right. So what I showed in this slide is the important metrics, right? And what I'm saying in the next slide is, if you look at the below problem, it's the same thing. What I'm saying is these are three metrics that are important. But even within these three metrics, we care for improving viral actions, but at the cost of not decreasing EFS and not decreasing job applies. That's what the below optimization problem says. Does that make sense? So basically, let's say you have you have a dynamic system like a feed. You can have multiple metrics you care for, right? But then among all the metrics you care for, there is a true north which you really want to improve, which is again a business choice. And you say, okay, I want to improve this, but I don't want to decrease things I care about, which is job applies and EFS. That's all the below maximization problem is saying. Does that answer your question?
Yeah, that makes sense. Is there a practical example from LinkedIn page itself which can enumerate this particular use case, or that's more?
No, this is just okay. Thanks for asking that question. I think so. This is when you say practical, I think these metrics are what we really care for on the LinkedIn feed. Now,
Okay.
so to frame it right, like for what's happening is this: so many people who are going to LinkedIn are getting their feed experiences. Every individual member is getting a feed experience. Let's say there is 20 items that you see. In maybe at the back end, we are scoring 500 items, and the top 500 items. Of course, we go and fetch maybe 5,000 items. but that's the level of detail we don't want to get into right now. But let's say the last layer, very last layer, we score 500 items. So let's say for Viral, we are scoring U from U1 to U500, and that's what this upper uh, equation is doing. So given an item, we featureize it and we score a V probability of a viral action model. We score probability of an EFS and we score probability of a job applies. Now, of course, if the content is organic, probability of job applies is zero, right? Now, once you have scores of those 500 items, you just sort and you show me feed. Once you show me the feed, I'm going to perform some actions, right? I'm going to like something, I'm going to comment on something. These are all viral actions. I'm going to have a good feed experience that will increase the EFS. So when you interact with the LinkedIn feed, there is some events which are asynchronous events which are pushed into the LinkedIn system, and that's how we see when I serve you a feed. There are metrics that are computed, which are across all the members. Now, let's say for all the members, now this is a hypothetical thing, but all the members in US Chicago, I'm using a choice of XEFS, XJA equal to XEFS equal to 1 and XJA equal to 2. That will lead to a particular kind of ranking, right? And hence, which will affect how viral actions are computed, how EFS is computed, and how job applies is computed. Because based on XCFS and XJA, the ranking changes. Let's say the jobs always show up at the end. So the job applies metric will automatically go down. Hopefully that was clear. If not, please ask. Um,
Yeah, I think it's in. Yeah, I think we can move on. Thanks.
cool. So now what I'm getting into is, so this is slightly a little bit of math, but please ask me questions. I'm happy to answer. Um, so please keep in mind, there are two things going on over here. Um, One is the metric, which is capital VA, capital EFS, and capital JA. The other is the machine learning models. And these two are totally different, right? And I'll give you a very concrete example. Let's say the metrics you care for is revenue, right, as a product, but you will not build a machine learning model for revenue. You'll build a machine learning model for probability of a click. And you know there's a correlation between click and revenue. If I can get more clicks, it will translate into revenue. And sometimes it's easy to build a probability of a click. Revenue is also very noisy, and it's hard to measure over a you know intraday or over a few days. Revenue is something you may measure across a week, right? So not necessarily every metric will have a machine learning model. And that's what the role of a machine learning engineer is. How can I improve my business metrics? By choosing the right models I want to build. I'll go to the next slide. If you have any questions, please ask. So the top portion of the slide shows viral actions, which is again a metric, just to make it clear. What I'm saying is I'm modeling these viral actions via a latent function, which is f of VA. And similarly, other metrics as f of EFS and x of GA. Below what I'm doing is I'm saying maximization problem that I showed you in the previous slide at the bottom. I'm just changing this function thing because these are raw numbers, right? Viral actions is a raw metric. If I want to optimize it, I want to smooth it. And that's why I'm creating these latent functions. I will explain you uh, how do we model these latent functions in the next few slides. But I want to get the formulation correct, and so that once we get there, we are not confused within us. So the leftmost side, what we are saying is maximize viral actions with the EFS and job applies having some constraints that they should not be less than some constants, right? Now, I just converted those viral action metrics to a latent function, f of VA, f of EFS, and x of JA. And the last point is saying, if you look at the second point, it's saying you can choose any x, and as long as that x satisfies these below two constraints, that x is a valid x, right? Now, I'm just, as a notation, I'm just simplifying my notation. I'm saying my choice of x is a constraint space where these constraints are satisfied. So that capital X is a constraint space. That's all we are doing. Any questions on this? Because, and I'll tell you why we did the last piece, because now I've simplified that problem and mapped it to a regular math problem which we can solve. That's all we are doing. So the goal was to take a real world problem and how we can map it to a problem which we understand we can solve in a textbook.
Got it. Makes sense. Viral, is there a possibility like to show a LinkedIn feed and a LinkedIn page and how that is correlated to this formula, or is it like we?
So, okay, I think, see, one thing to, thanks for that question. So one thing that's happening over here is, uh, these metrics, viral actions, right? These are computed over several members. Okay. If I compute this viral action metric over a few members, it will have a lot of noise. It will have a lot of variance, is what we say, right? And I want to, and hence what we do is, let's say, in my all the members. So LinkedIn has about maybe more than 1 billion members now. I will have maybe at most maybe 14 choices. And I'm just throwing a number, but 14 choices of X is a two-dimensional parameter, right? It has XEFS and XJA. So I just have 14 choices, right? So what is happening is I'm computing VA values, which are there are 14 VA values. So if I go and show you my LinkedIn feed, it will there is no easy way to map it, because the viral action metric of people who are exposed to a particular choice of X, so let's say X equal to 1 and X equal to 2, is all the members in India and all the members in US, let's say. We will compute the viral action metric, and that will be one data point.
Got it. So the viral actions are those emojis which comes on the
No,
like button. No,
viral
no.
actions is whenever you look at the feed, you
Okay.
like something, you comment on something, or you share it again.
Those three attributes. Those three scenarios. Okay.
Primarily, yeah. I think emojis also. I'm sorry. Yeah, I think
Mhm.
whenever you interact with the feed, you're creating an act. You're doing an action, and that action uh, flows into your people whom you're connected with, their feed also. So that's why it's called viral action. You're taking an action, and it increases the virality of the LinkedIn feed.
Got it. So in certain cases, folks, if somebody is looking for a job, they tag saying CFBR as a tag to promote that particular feed. Is the reason being like it gets viral because of a lot of people commenting an hashtag for a
Absolutely. When you go and share something, but when you go and comment on a feed, people whom you're connected with may get notified, and that's where the separate product called notifications comes into picture. So both feed and notifications are two content distribution channels, where feed's job is to improve your experience once you're on the platform. Notifications job is to bring you to the platform when you have good engaging content that you can consume, and they both need to work together in order to improve the member experience. That's a great
Got it.
question. Yeah.
But the user need to be connected, or the user has to follow that person.
Perfect. Yeah, it can be connected, it can be follow. Sometimes it can be also someone whom you do not know, but you're highly interested in that content. It can
Okay.
also be that.
Makes sense. Yeah.
Yeah.
So
But hopefully
I
that's okay, sorry, go ahead.
yeah, I just have a question like this maximizing viral action. Uh, is it like uh, demography wise we can change it, or is it for
Yeah,
the entire globe one, or how?
yeah, that's a great question. I think for for in reality, yes, we can solve this over different cohorts of members. But to keep it simple, let's say I don't break my members by, whether they are, let's say, from a certain geography, but I just randomly assign. I say, like, okay, for simplicity, let's say X is a one-dimensional. Okay, X is a two-dimensional parameter. We all agree, right? X EFS and XJ. Now I just choose 14 different values of this. Let's say 1, 1, 2, 2, 3, 3, 4, 4, up to 14, 14, right? There's no reason why we should choose such weird values, but let's say we choose them. Now, all I say is among my 1 billion members, I will just randomly assign 1 billion divided by 14 to each of them, right? So a given choice of X, EFS, and XJ, we'll be using that choice, and we'll be serving how many members? So 1 billion divided by 14. Like what? Assuming 1 billion is our Indian member base, right? So all those members will be served with a particular choice of X, and we know a given choice of X influences the metrics. So for that choice, for the first row, where X is equal to X EFS is equal to 1, XJ equal to 1, we will get VA, which will be an aggregation of all the metrics of all these members who perform the viral action. So all the people who are exposed to X, we will count their likes, comments, and shares, and that will give us one value. Similarly, we'll count for all these members the EFS, and it will give us one value. So basically, if you look at the data, finally, you just will just have 14 rows where you have some X's in each row, and you have VA, EFS, and GA. Actually, let me quickly show you. This will, I mean, maybe it helps. Uh, yeah, you see this?
Yeah.
Let's say this user who got exposed to a parameter set S1. Now, S parameter set is nothing but X EFS equal to 1, XJ equal to 1. You can think of
Yeah.
it. Right?
Okay.
And that person did some impressions, some clicks, some engagements. Now, this is not a feed problem, this is a notification problem, but everything applies. So now if you see, so many members came, they did some impressions, they did some clicks, they did some sessions, right? What I'm doing is, I'm saying, okay, I don't care about every member. I care about a given parameter set S1. What was the total metric? Total number of impressions, total clicks, total sessions. Is that clear?
Yeah.
So if you see the left, this table, there are only three, S1, S2, S3, and hence that's why there are only three rows.
Okay. As far as the model is concerned, machine learning
Yeah.
model, will there be a one model, or is it for each kind of behavior we will have?
Sure. So there are two things going on over here. There are there are two models, two kinds of models. One is this called what we call as utility models. These are
Yeah.
purely optimizing for viral actions. Okay. It's a
Okay.
supervised learning problem. You know, when I serve you a feed, you may or may not perform a viral action, and that will be my positive or negative label, and I will train a model. Right now, there are obviously more complexities to it, but to keep it simple, um, given I serve you a feed, and given you impress on it, or maybe given you click on it, I want to know whether you liked it or commented or shared that thing or not, and that will be my positive or negative label, and I will train a P of VA, which is this model PVA, right? Similarly, PFEFS can be trained in the similar way. We know labels. These are all supervised problems, right? But now, how do I efficiently find what is the right choice of XEFS and XJA? And that itself is a machine learning problem. And I'm going to, my goal of when I say tuning recommendation systems, it basically means how do you choose those XEFS and XJA in a most efficient way, where you don't have to spend a lot of time, and you can quickly identify the right operating point for the ecosystem, and ramp it to your members.
Okay. Got it. Thanks.
So cool. So if all of this was clear, I'll just quickly jump into notifications problem. And really sorry for in the beginning we couldn't get those things sorted, but I already see it's 8:44. So let's just quickly go over some of these details. I'm not sure if we'll be able to cover everything, but now I'm showing you a separate thing, which is notifications. And like I was saying, notifications and feed both work together. One brings you back to the platform, and one improves your one. Once you're in the platform, the goal is to serve you good content so that your experience is better. So basically, if you understand this whole thing, what's happening for notifications is there's an actor. Actor is a member who will come to a feed, and he will share something. So you will go and you will type something and you will share it with people, right? Once you do that, people whom, so let's say in this case, let's say I go and share, I'm the actor. Once I press the share button, once I post on LinkedIn, it will create a notification. It will send notifications to people who I'm connected with or who follow me. Okay. So you can either get a badge notification. Badge is, right, when you see the app, you see okay, actually we show it over here, right? This is a badge. Or you can have a push notification. And this is how the LinkedIn tab looks. Now, when this is how the notification tab looks. Now, when you go and interact with this tab, you will click on a notification, and that is sort of a positive or negative label. If you impress on it and you don't click, it's a negative label. If you click on it, it's a positive label. Now, just as we were looking at feed for notifications, the metrics we care for are sessions, clicks, and volume, send volume. And why send volume? Slightly tricky. See, you can always send. So today, let's say you're sending 100 notifications, right? And you're getting these sessions and clicks, right? Tomorrow, what you can do is, hey, I want to just optimize for sessions and clicks. Let me just send, instead of 100, I send 1,000. Now, obviously, when you send 1,000, people are going to come, but they will be also pissed off. Some of them will, shut down the channel. Some of them will close the app, right? So we have to be cognizant of the right volume we want to push. So the experience we want to do is, like I show below, you want to be able to improve sessions. And sessions is nothing but once you click on a notification, you open the LinkedIn app, and that is a session. You want to be able to improve clicks more than some constant, but also you don't want to send notification volume more than something, right? So hopefully the bottom optimization problem was clear. And now in the top, I'm showing you the machine learning models, p-click and p-visit. P-click is optimizing for clicks for a given member in an item. P-visit is optimizing for whether a member will come to the platform if I notify the member. And XTH is a threshold. All that means is, given a content, if I go back to the experience, in this case, when I went to the LinkedIn feed and I shared something, Bharat, who is connected with me, we will actually score this. We'll say, okay, probability of a click for a member M equal to Bharat, U equal to that item which I shared. I'll compute this p-click score. I will I'll apply some X alpha. I'll compute the p visit score, which p visit is a machine learning model. And I will say, okay, if this thing is more than the threshold, XTH, I will send this notification, else I will drop this notification. Was that clear? I'll move ahead if something is not clear, please stop. So again, this is two hyperparameters, X alpha and XTH. Just as for feed, we had those EX, EFS, and XJA. Here we have X alpha and XTH. And basically, what this slide is saying is, choosing this X or the tuning parameters is hard. And the reason is, whenever you change your machine learning model, let's say you have a team of 20 people, someone in your team goes and changes X p-click. Now, because p-click has changed, the score distributions of p-click have changed, and hence, I have to now retune what my X alpha and XTH should be. Right? Also, when I add new content to the platform, it will have very different distributions, and hence it can also cause shifts, right? So traditionally, what would happen, right? You would have a machine learning engineer who would, let's say everything is stable today. I'm a new engineer who joins the team. I train p-click. Now, for me to take that model to all our members, what I have to do is I have to find X alpha and XTH. So what I'll do is, okay, I'll choose some choices of X alpha, XTH. I'll run a bunch of A/B tests. I'll monitor those tests, and one of them is better than the stable experience or the control, and that is what I will roll out to all my members. Right. So as you can see, if someone is doing that, there's a lot of human in the loop. And can this be automated? That's the problem we want to solve. And there's a whole bunch of things that we can discuss. I'm just thinking whether we have enough time. I don't want to be in a place where I start something and we have to stop. So Bharat, why don't you tell me, is 9 o'clock a hard stop?
No, it's not an hard stop. Since it is Google Meet, we can go on for some.
Okay.
more
Okay,
time. I think folks will stay interested. Folks will stay on the call.
okay, fine. And let me know again if something is not clear. I think I want to make sure I totally respect 8 o'clock in the night in the evening is not you know not everyone is here on the call, so certainly you guys are interested. So I want to make sure you get the best out of your time. Please
Yeah,
stop me. If something is not clear, stop me at that
yeah.
point.
I think the session is interesting. I think go on, Vaidali.
So now a little bit of math, but hang tight with me, and hopefully this becomes clear. And this goes back to, if you remember, I showed you the table. In that table, I was showing you there are different members and there are metrics computed per member. But what we really care is we care metrics computed per choice of hyperparameter, which is a given x, a given choice of x, right? Each choice of unique x's, we want to compute the metrics, and that's why there were two tables. The second table had only three rows, if you remember, right? And now what we are saying is we are just formalizing it. What we are saying is think of a member I and a notification J. And at this point, I'm strictly talking about notifications product. So forget feed for the moment, but everything applies. We can always change this to a feed content. That J could be a post. And for a member I and a notification J for a given metric, let's say clicks, let's say K is clicks. Okay. What we are saying is, okay, you will either click something or you will not click something. That's all it's saying. So Yij is an indicator function. And all I'm saying is for across all the members, I, and across all the notifications, J, that was served to members that was served for a given choice of X. So let's say again, going back, X alpha equal to 1, X threshold equal to 2. That unique choice of X, all the members and all the notifications, I'm computing, I'm saying the sum total of all the clicks is my left hand side. Okay? And that number is a Gaussian distribution with a mean of f of x, and it will have some noise, obviously. We, we are looking at an empirical metric value, and it will have some noise. And so I'm modeling that noise by sigma square. And the next step is all it is saying is that mean of f of x itself is a multivariate Gaussian distribution which has a mean of 0 and a variance which is a kernel, which is a radial basis function, a k RBF. And it seems tricky. It's very easy to understand. Let me give you an example. And for simplicity, I will say, if you look at this function, the score, right? If I simplify the score and I say p click greater than threshold. So let's say I have one machine learning model, p click greater than threshold. X alpha is gone. Okay. So now your hyperparameter is one dimensional. That X is XTH. Simple. Okay. All I'm doing now is I'm saying, so what does that mean? Think about it. If my threshold is 1, and if I continue to increase my threshold, I will send less and less notifications, right? Because p click has a certain distribution, and as I change my threshold, there will only be some notifications which will be more than that threshold, right? Fair. Now, as I do that, obviously my metrics, which are sessions, clicks, and send volume, they will be very different because I'm serving different notifications. I'm serving less quantity, right? At each as X threshold increases. Are you all with me so far? I'll take it as a yes. And all I'm saying is this. Think of X equal to 1 and think of X equal to 2. Simply two rows, right? For X equal to 1, I'm saying there is a metric value I compute. And for X equal to 2, there's a metric value I compute, right? And these two are correlated. Why? They cannot be very far away from each other. They have to follow, they have to be related to each other because as I increase my threshold, I know my metric will my clicks will hopefully go down because I'm sending less notifications, right? So they are not like random numbers. They follow a certain pattern, and I want to basically model that pattern through this kernel, and I will learn the parameters of the kernel. If this is not clear, please ask questions. I'll take it as a yes. Actually, let me show you something. Uh, yeah. So let's look at this. This is a plot, and of course, it doesn't have numbers because we don't want to reveal uh, some sensitive data. But if you see this, right, there is a red. You see these red numbers. You see this red line which is hidden behind the blue line.
Yes, yeah.
Raw metrics. So all that is saying is for a choice of, let's say, 0.1, which is a threshold, I have a certain clicks. Now y-axis doesn't show you that number, but as you can see, as I increase my threshold, right, I see the clicks going down. Do you see that? Because he is, yeah, right, and that is very obvious, right? So as you can see, this red line has a pattern. It's not random. It is not like it is going crazy here and there, right? And those blue lines are my models. They are predicting the value of those red points or anything in between those red points. And this is a generative model. And there are three blue lines. The middle blue line is the mean function, and the surrounding two blue lines are variances around that mean.
Yeah, well, what does that red indicate?
Red is a pure data. What it means is for a given choice of point 0.1, let's say point 0.1 was a threshold we used for a billion members, or sorry, a million members. I'm computing all the clicks, those million, those specifically x equal to zero point 0.1 members, all those members who were exposed to that x equal to zero point 0.1. I'm computing the aggregate clicks, and that's the number.
Makes sense, yeah.
It's a pure data, right? If that is clear, right? I think it's this we are really in a good shape now. So now this slide is similar to the feed slide. There is nothing else going on over here. You're just saying sessions is f session. These are all latent functions which are similar to this, whatever we have over here. So I'm not going to go over it again since we've already covered it. So now this part is a little mathy, and I can go over it, but let me see if I can basically, okay, let me see. So now you remember we were saying this thing, maximize f of x where x is in some constraint space. Now we start using that thing. So now this is textbook math. Maximize y of x. Now this y and like all of these variables, please forget the context of previous slides. These are generic. These have nothing, no bearing on the previous slides. You have a function max of y of x, and you have some constraints. And all basically you can say y of x. If you see, this is nothing but what we discussed. Y of x itself is a Gaussian random variable, which has a certain mean and a certain variance. And f of x, which is a mean function, is itself a Gaussian random variable, which is defined by a kernel. And this is what we discussed, right? The mean, the mean itself is a function, right? So it's basically, you can think of it, right? Once I'm able to learn this, right, I can give a choice of x, and I will know what is my f of x, and that's why I say it's a generative model. Okay. Now the below two things, forget about, like, just focus on the Gaussian. The below two things are saying like, okay, if my data is a binomial distribution, I will basically model it as a binomial, but that doesn't matter. We'll focus on Gaussian, and then similarly let's pose on. Okay. Let's see.
Well, just a quick question. What is the PMMK with there
Which one? This slide?
in this slide? The invitation rate in PYMK. What does that denote?
Oh, I'm sorry. Yeah, PYMK. Yeah, PYMK is a product called People You May Know. So this is just so. I mean, if you look at, right, even Meta has you will connect someone. You connect to someone, right? You can go and you can send a connection request, right? So that's the product PYMK. People you may know. LinkedIn college calls it PYMK.
Got it. Okay.
Yeah. Uh, Here what we are doing is this problem. We are simply taking a Lagrange over here. And let me just go over this quickly because I already see it's 9 o'clock. And I'm happy to, set up a separate half an hour if people in this room are interested. I understand this is a complex topic, especially, if someone is exposed for the first time. So, totally, please feel free to reach out as well, right? After this. Uh, Let me just go over, let me just quickly
I
show
have a,
you.
I have a different question. So right now, the post impressions which shows on LinkedIn,
Mhm,
check out who's engaging with your post.
mhm,
Let's say if I'm looking at my LinkedIn right now, it says 1,400 post impressions.
mhm.
So those are impressions wherein people, though they don't click on the like button, but they come to the feed and
Mhm.
just taking a look at the post, even without acting on the feed. Those are impressions, is it?
So even if you click on something, there is an impression you're making, right? In
Yeah.
order, you have to make an impression. So if you have to, so there is at least 1,400 people who looked at your post. Some of them may have clicked, some of them may have even interacted with your content, liked, shared, or commented.
Okay, let's say there are 60 likes or 10 comments. So
Sure.
the active connection, the active participation was just 60 plus 10, right? Like 60 people clicking the like button and 10 people commenting on the post. But
Yes.
the impression says 1,400.
Yes.
What does that denote for the person who's looking at the does it mean like there are 1,400 people have definitely saw this feed?
That's right. Yeah.
Okay.
Yeah. So, okay. So I'll just quickly, I think, okay, maybe the most important piece, I think if you understand these two tables, right, I think you kind of can, connect the dots. Basically, we are those Gaussian functions that I showed you, or those kernels that I showed you, we will learn the parameters of those kernels only on this bottom data set, which is a very low, we talk about big data, right? No big data, 50 rows, 100 rows, right? That's the scale we're talking about here, right? And that's why these functions need to have certain properties, and that's why we're using Gaussian, right? So, but yes, there is big data. The left-hand side table will be massive. Think about every user, or not even every user, every action is a separate role, right? And then you aggregate it across users, and then you aggregate across parameter set, and that creates your bottom-most table. So this is the most important piece. So if you look at this whole system, how it is designed is you have an offline component, and each online system can be very different. So I built the system at LinkedIn for a bunch of use cases because, as you can see, these problems are very common. Any big recommendation system will have a bunch of machine learning models. How do you combine these models? Is a very common problem, right? That's the abstraction we are talking about. So the serving can be very complicated and can be very, very specific to a system. Feed will have a very different serving architecture. Notification will have a different serving architecture. Ads will have a very different serving architecture. So we don't want to get into that business. We say, okay, why don't you take parameter choice, which is again different unique values of parameter choices, and store it in your system somehow, and then serve it to your members. And when the members are interacting with something and they're creating those metrics, just publish those tracking data on a Kafka topic. And we will aggregate that and we will learn this over here in this yellow box and we will update it. So it's a classic explore exploit. I will start with, let's say I know, again, X threshold. Let's take a single dimensional search problem, right? I know X threshold. I do not want its value to be more than, uh, I want its value to be between zero point 0.1 and 1. Okay? Because if I simplify the problem, peak click greater than threshold. Peak click is a probability. Probability is between 0 and 1. So I just want to search for X threshold between zero point 0.1 and zero point 0.9, right? So I can say, okay, randomly just, look at this metric, let's say clicks or this metric sessions, at different choices of X threshold. So I can randomly pick 5 points at which I look at these metrics, and once I can fit the function, I know where I can where I should search for my next point. I will be confident about some points, I'll be less confident about some points. That's why we are modeling the variance as well. And that's why I showed you those blue curves, which was 3 of them. So basically, it's a classic explore exploit. Collect data, understand the surface, then collect more data, and you will slowly converge to a choice where you want to, where you can say, okay, this is the best choice. And then you will turn this on for all the members. So I think I want to stop here. But if you have questions, please ask. There are a few things we couldn't, but yeah.
Yeah, so yeah, so basically we are using this machine learning model to detect what
Yeah.
parameter.
Yes.
I mean,
Let me. Yeah. Thanks for asking that question. I think we are using this machine learning model for this. If, let's say, I only have probability of a click in my ecosystem, let's forget p visit for a moment, right? If I want to change p click, let's say I add 100 features to it or 10 features to it, I train that model. That model will have a different score distribution. Now, what is the choice of X threshold I should pick? I don't know. And that's the problem we are solving. All of this machine
okay.
learning. So can I just say, I care about these metrics. I define these metrics. I define what is C clicks. I define what is C send volume in a JSON, and the system that we have built ingests this JSON and then can quickly spit out some values of X threshold and do it in an explore exploit fashion and converge to a right choice of X threshold. So what happens is, now the job of a machine learning engineer is to just write down that problem, what he cares. Problem is, I care for sessions, maximizing sessions. I care for clicks, not greater than C clicks, send volume less than C send volume, right? And I just start this. I just click a button, and this whole system will automatically identify what is XPH. And I don't have to go and run multiple A/B tests as a machine learning engineer. And if you look at like places like Google, Meta, they all have such systems built. Uh, and yeah.
Okay. So how often we have to the model we have to retraining, and all? How often you?
Your question is, how often do we have to retrain? I mean, it's, if you look at it, right, that purely is a function of, like, let's say if you have a team of 20 engineers, each of them is training models, right? Each of them is having some ideas, uh, and they're trying to improve the model with those ideas. So you could say, as many engineers you would have, as many p clicks, and each of them wants to try to find a choice of X threshold, and whichever experiment shows better results on top of control, you will take it to all the members, right?
Okay. So during this retraining, how the disruption happens? I mean, how the traffic? I mean, our service basically will it get affected?
So model training is an offline task, right?
Yeah. Okay.
Whatever you are doing online will continue to happen, right? Like you will just add 10 new features and train a new probability of peak click model, right? Now,
Mm,
if you want to take this peak click model online, you will have to say, okay, I will take 1% of the traffic, and for 1% members, I will start an experiment
mm,
where I will use this tool, which will help me find XTH.
okay.
Once I find the right XTH for that 1% members, I can now I can look at the metrics and say, okay, 1% versus 99%, right? So a clear A/B test, and you can clearly see 1% for that 1% members, you're beating the metric, and so you slowly ramp that 1% higher, and to like maybe 20% to 50% and 100%, and yeah.
Okay. You said A/B test. No, I I heard that term few times. Can if you don't mind quickly can tell what is A/B testing?
Oh, okay. So A/B testing is how do you statistically check uh, whether a particular experience A is better than experience B. Experience
Oh,
is driving some clicks metrics, right? Experience B is also driving some click metrics, but each of these metrics have also variances. So how do I know whether A is better than B? And you basically run an A/B test to know which one is better, statistically significant, because two things can be can have different values, but they may be similar because the variances of these metrics can be really high. And so typically, a lot of internet companies will have a tool which will allow developers to just simply run A/B tests.
Yeah, thank you.
Sure. Uh, any more questions?
So do you see a, I mean, transformer model? If, I mean, is
One
there
minute.
a use here? I think no, no.
Sorry, what did you say? You said transformer model.
Yeah, yeah,
So transformer, do you mean like the transformer architecture?
yeah.
So the transformer
That is
architecture,
basically in LLMs. They are all based on transformer.
yeah. So for example, let's say probability of a click is a machine learning model. Instead of just instead of it being a very simple model like a logistic regression or a deep neural network or a simple deep like a wide and deep neural network, it can be a transformer model. So all those architectures can all be, you can kind of have different p clicks, and that's why, right, when you say how many p clicks, right? So for example, one engineer in a team is trying to use sequence modeling and say, okay, I want to look at the last 20 sequences and predict whether on a new item member will click or not, right? So they will use maybe a transformer architecture. So that's okay, also a p click, right?
Yeah. Thanks.
uh, any more questions? Yeah, Bharat, happy to
Yeah,
uh,
yeah. Well, I had a quick question. So, um, do you have any references for the audience to learn these different ranking functions, or these are very common concepts? Do you have any references for us for good read through in a bit more detail?
I mean, I can definitely share some. Uh,
Okay,
um,
that will be fine. I think if you can offline share.
yeah,
Yeah.
I'll share something. Yeah, anything else?
No, this is a very interesting session. Thanks, Viral. I think folks can reach out. Will you be able to share this slide with us? I will put it on the Google Drive and then put it on a speaker's deck and share it with folks.
I can share it.
Yeah, sure, perfect.
I mean, I can convert it into a PDF and I can share it.
Yeah, you can do it in a PDF. Yes.
Yeah. Okay, that sounds good. Okay.
Yeah.
Thanks for sticking along, and yeah, totally appreciate so late in the evening you could join.
No, no. Thanks a lot. I think
Thanks
thanks
a
for
lot.
the nice session.
Thank you for your time. Yeah,
Yeah,
great session.
yeah. Take care, guys. Yeah, bye.
Thanks.
Thank
See
you.
you.